Okay, so I love automatic contact modeling. I'm impressed it does it as well as it does. But I really don't care about the tires. I don't really care how they're going to rotate. What I care about is the inertial state, the acceleration I put the vehicle in, and the forces that basically are created by that acceleration. Basically the response of the vehicle to it, especially when it begins to tip over. That's really important, of course. So, anyways, let me introduce this shortcut, and I'd love to hear from you and see what you guys think about this. So I call it a motion platform, and the basic idea of this is, let's go here. Let's create kind of a rectangular block, a slab, right, and then let's give it the dimensions of our vehicle, which I believe is 1.8 in X and 1.5 in Y. And so think of this as really a projection from I'll call it from above or whatever you want to call it, of that shape of the vehicle. And so this third dimension, we just make it small, 0.05. All right, so it's you all. Let me get into the basic idea now. Actually, I want to put this at the center. All right, so that's like right there. All right. And the basic idea is that three constraints are necessary to stop this thing from moving. All right, and obviously right now it falls due to gravity. All right. All right. So I'm going to put these frames here. I'm going to put one up here in the center, and I'm going to put two back here. And I'm going to really associate these with what I'll call the front axle and the rear axle. All right. And so back here, I'm going to match those locations. So it's still kind of fresh in my mind. Mine is 0.65 on X. The width is 1.5, so half that. Oops. I think this is positive. Yeah, of course. All right, and again, we get Z for free. So let's match this for this frame. This time negative. All right, and this one will be kind of between the two front tires, and therefore it's even easier, 0. And that the position along kind of this X is 0.58. All right, so these are just coordinate frames. They're just kind of markers, attachments. It still falls with gravity. All right, and so the basic idea, though, is, and I'm going to do this to the ground right now, but essentially we're going to attach to the vehicle through these three coordinate systems. And so if this one's a spherical joint, oops, I got one more thing to do. All right, I'm going to get all three of those chords again. I want to get to world position, and I want to match the orientation. Because as we move into Simulink, these are going to be kind of the orientations will be used there, and we're going to do all kinds of measurements through these coordinate frames. So again, there's convenience in matching the world orientation. Of course, at Simulink, you can always do the math yourself, but math is hard sometimes. Okay, so anyways, with those all set now, I think I am ready. So let's put it in the spherical joint. Great. And with that, we would get this kind of motion. It just kind of flops all over the place. All right. Okay. Now I've kind of referred to that this is going to, these two will kind of act as a rear axle. Let me prove that right now. And so with that frame, I'm going to connect to the ground. Let's do that right there and there. And this time it'll be a rigid joint. And from here, let's zoom in. Let's turn this cube into rotation about all axes, and then let's let it slide along Y also. Can you see that little green line there? All right, that means it can slide about that axis. All right, so let's view all again. So instead of flopping around all over the place, it's essentially rotating about an axis that's been set by those two constraints. All right, and so then this last one, this is essentially going to be our front axle load. And this one, Again, I like this idea. So let's create a rigid joint. Zoom in. All right, and constraint. And this one is, again, rotate about all. And then we got X, Y, and Z. Oops. X and Y. All right. See the two lines. All right. So it's very similar to the way we connected the load to the forks. All right. And again, just proving it to you, we'll see that that stops the rotation completely. All right. So anyways, but to bring this into our forklift model, let's change the name of this to motion platform apply. All right, and let's get rid of the 3 joints, as well as we'll get rid of the 3 connections to the background that took place when we created the joints. So I'll get rid of these 3 too. Okay, so what I want to do is copy all of this and paste it into our model of the forklift. So do that again. It's just keyboard Control C to copy. Sorry, it's right there. All right, and let's paste it in. All right, and let's hide everything. Except the vehicle, so it's hide all others. I guess I want to show the platform too, as well as the 3 frames. Okay, and you can kind of see they're lined up in X, but their Y is off for sure. So let's go here, and we'll see the position of that vehicle, and Y is that number right there, and so I'll copy that. It looks pretty good. It's pretty much underneath. Now we just need to raise it up. And you'll recall that this is 2 meters high. So that Z position of 1.45 means that 1.45 minus 1 gets you to that bottom surface. And we'll bring this up. And there's a little math I'm going to have to do. Let's see. So this will be 0.45. All right. And again, the thickness of this, let's zoom in a little bit. The thickness of this platform is 0.05. And so I think, very conveniently, I just have one more digit, and that sets it up like that. All right, perfect. All right, so it's in position, but there's really no connection. I hit run. All right, we remember that the vehicle itself was fixed. So we remove that. They both fall due to gravity, and so let's put those attachments in now. And I think I'll do this in wireframe, so I can be very kind of conscious as I do this. I'll show you. I do want to check one more thing. So let's visibility show all. And yeah, indeed, that is the front axis. These are the rear axis. And timeout. I'm going to go fix these. Okay, I'm back. 2 fixes. I don't know if you guys caught it in the previous video, but I put these right side ones at the same position as the fork. I intended them to be at 0.75, so we fixed those there. And somehow I kind of put in that last coordinate wrong, and I just moved it back to the minus 0.65. So anyways, hopefully this is a good enough visualization where you can kind of see it. But selecting the 3 frames on the platform, they show up, as squares here. I think you can kind of see they're matching the axle connections. So anyways, I think we're ready to go, right? And so let's go back to shaded, hit run. That's kind of where we are right now. Everything's moving. And so let's create the joints first. And so we'll do this in wireframe. And I think all I want is really this stuff, and holding my control key down, this time select the vehicle and visibility, hide all others. All right, and so this frame plus the vehicle, that will be my spherical joint. Great. This one plus the vehicle. All right. Again, I'm going to do my trick, rigid joint, create, and let's zoom in. Okay, and constraint page, and they will rotate about all, and they will slide along the y-axis. Perfect. All right. And then this one, that's going to be our front axle. And probably between now and getting this to Simulink, I'll change names so you'll see words like front axle. But let's see. Selection on that in the vehicle. Motion model, rigid joint, create, and constraint page, rotate about all, and slide in the X and Y direction. All right. And so our platform is now officially connected, and connected in a way where we can make force measurements that will give us very useful information with regard to the loading on the two axes, as well as how much is on the right and how much is on the left. All right, so let's go right mouse click, view all. And the last piece here is really, let's put this platform in motion. All right, and so we want to move it in the X direction, put it on the platform. I don't want the vehicle there right now. All right, so let's do that again. Put it on the platform, position 0, 0, and instead of even being on the top surface, I'll put in 0 there too. Right, and world position, good idea to have this oriented with the world, and so I rotated about that Z axis. Right, and with that, I'll create a connection with the world, rigid joint. Okay, but I'm going to do a few things this time, a little bit different this time. I'm going to click on this. I'm going to set it up so that it can slide in the X direction. And then I'm going to turn this into an actuator too. And so linear actuator right there. And here I'll use kind of the formula creation capability of the SimWise tool. All right, and so velocity, I'm going to set that up with their formulation tool. So I don't need to go to working model, I'm sorry, to MATLAB to set this like I did in working model 2D. All right, so I want the initial value to be 5, and I want the final value to be 5. I'm sorry, the initial value to be 0, and then 5 meters per second. I want the transition to start at 1 second, and I want the transition to be done by 3 seconds. All right. Now, I practiced this in between videos, and there's one other thing I'm going to fix. All right, and it says rack SWAT. All right, so let's show this. All right, and just to remind you what it connects, we'll select these two guys too. All right, and you'll see somehow that SWAT got set up so it's kind of pushing right to left. And I want to go up and down. And it's got kind of reoriented, again, this idea that I really like everything to be, well, I'll say everything, I'll say my preference is to have things lined up with the world. I'll just kind of line up these two guys. So the two frames are making up that SWAT joint. I'll go to world position, and I will set that up 0, 0. All right, and I think that will allow us to get what we need now. And I'll go right mouse click, sorry, show all, and then under view. Let's look at the shaded again. And let's look at it. I hit I on my keyboard, puts me in isometric orientation, and I'll hit run and we'll see how we do. Clock's right there. All right, it starts moving at 1 second. Smooth transition. So it starts off kind of slowly. And I'm going to run it to 2 seconds because that's when the forks should start going up too, which they do. All right, so I retained that formula that came from Working Model 2D. All right, and why I don't worry too much about these formulas, because once we get into Simulink, we can create whatever formula we want. So, and we're really good at that on the MATLAB Simulink side. So anyways, thank you for watching.